this unit is going to focus on another type of chemical reaction that we'll discuss, which is known as redox reactions. We've spoken previously about precipitation reactions, acid-base reactions, and of course textbook goes into gas-evolving reactions. Redox reactions are any reactions that involve the transfer of electrons. Okay. Now, as the name implies, as the description applies, there's a transfer of electrons. So something is losing electrons and something is gaining electrons. So there are really two sides of this reaction, or two half reactions, as we'll call them. There's an oxidation reaction and a reduction reaction, and these are generally just referred to as redox reactions to shorten up the title. Okay. Now it turns out that there's a variety of chemical reactions that are actually redox reactions. Any reactions with oxygen, whether it be oxidation of a metal to form a compound or the combustion of an organic molecule with oxygen, is a redox reaction. There is a transfer of electrons from one atom or one element to another. Here's one example of hydrogen burning in the presence of oxygen is a redox reaction. Okay, so one of the goals that we'll need to discuss today is to try to figure out which species is gaining electrons and which species is losing electrons. Okay, for other reactions, such as say this, the reaction between sodium and chlorine, it's very easy to determine where the electron transfer is occurring, what's gaining, what's losing. We know that sodium has 1 valence electron, chlorine atoms have 7 valence electrons, so sodium would like to lose 1 electron to form a sodium cation. Chlorine would love to gain an electron to form a chloride anion, and so they're going to make the ionic compound. So you can very easily see that sodium has lost an electron, chlorine has gained an electron. Okay. That isn't as easy to see for our example with hydrogen and oxygen. We don't know right off the bat which species has gained electrons or which species has lost electrons, because we haven't produced any ions. So we're going to develop a system to determine that for these types of reactions as well. Okay, but first we'll talk about a little bit of the terminology between species that lose electrons and the species that gain electrons in a reaction. Okay, if we take a look at this, we can see that the overall reaction is written here in green. Sodium plus chlorine is yielding sodium chloride. We know that in the process of this occurring, sodium is losing electrons to form sodium cation, and chlorine, each chlorine atom, is gaining electron to form the chloride anion. Okay. We refer to any atoms that lose electrons as being oxidized. And any atoms that gain electrons, we refer to them as being reduced. Okay? A easy way to remember that is to ask Leo the lion. And when you ask Leo the lion anything, he says grr. And that's a little acronym for losing electrons is oxidation, and gaining electrons is reduction. So anytime you gain electrons, such as chlorine, we know that's reduction half reaction. And anytime you lose electrons, we know that that is oxidation reaction. Okay? So as we said, one of the first things we're going to need to do is determine how electrons are being transferred between species, molecules that aren't not ions. And how we're going to do that is we are going to assign oxidation states. Now, oxidation states are not actual charges. They're not ionic charges. Ion charges are real. But this is sort of like our bookkeeping for how many electrons are associated with an atom within a molecule. So if we can assign oxidation states for a given atom, and we monitor the oxidation state as the reaction occurs, we can determine if the oxidation state is changed, and if the oxidation state is changed, we know that there's been a transfer of electrons. Okay, so there's just a simple, a few rules that determine the atom's oxidation state. Free elements by themselves, so any of our monoatomic ions, sodium, gold, platinum, calcium, or any of our diatomic molecules, we're going to give those a oxidation state of 0. You can think of that the free elements haven't reacted yet, so they're starting out at the bottom with an oxidation state of 0. Okay? Monoatomic ions in any compound have their oxidation state equal their charge, or in aqueous solutions as well. Okay. The third rule can be split up into two subsets, but they say the same thing. The sum of the oxidation states equals the charge. So if you have a compound and the overall charge is 0, the sum of the oxidation states must equal that charge. The same is true for polyatomic ions. The sum of the oxidation states must equal the overall charge. Nitrate is a -1 charge, so if we take a look at the oxidation states for nitrogen in this example, which turns out to be +5. Each oxygen is -2, so 3 of those, so that's -6 plus +5, that gives us -1, equals our charge. Okay. Group 1 and group 2 metals in compounds maintain their charge, and again, that's because they are actually ions, and their oxidation state equals their ionic charge. And then lastly, for all other elements, determining oxidation states has to follow sort of this table listed here, and it sort of goes back to the electronegativities or of these species, or how much these individual species can attain an electron. Okay, so as we determine oxidation states, if there's a fluorine atom, it will get assigned a -1 first before hydrogen would be assigned a +1. So basically you go down this table and assign oxidation states in compounds based on this priority, which is based on the chemical reactiveness of these individual elements. Okay. So fluorine, always -1 first, and then another two that will really help us are hydrogen and oxygen. Before we label anything else besides fluorine, hydrogen gets a +1 and oxygen gets a -2. Alright, so here's all the list of the rules and the table to summarize. And what we're going to do is we're going to take a look at various redox reactions. We're going to determine the overall, or the oxidation state of each atom using these rules, and then we're going to determine what oxidation state has changed from the reactant side of the equation to the product side of the equation. Okay, so here's our first example. Here we have a combustion reaction, just like hydrogen plus oxygen in our first slide. This time it's going to be methane reacting with oxygen. Okay, so we know it is a reaction with oxygen. There's going to be a transfer of electrons. Our job is to determine which electrons, where the electrons were transferred, and then we can also say what was oxidized and what was reduced. Okay, so if we go through our list, we're going to assign a +1 charge to hydrogen before carbon. We know that the overall sum of the oxidation states has to equal the individual charge, or the charge of the molecule. Charge of methane is 0. Each hydrogen is +1, and there are 4 of them. So we can just use a little bit of algebra to determine that the oxidation state for carbon must be -4. Oxygen, O2, is its natural state, so this is a free element that gives us an oxidation state of 0. Okay. Using the rules, we know that we're going to apply a -2 charge to oxygen first before carbon. We know that this overall has to equal the charge of this molecule, 0. Because there are 2 oxygen, that's overall charge of -4. So now we can also use a little bit of simple algebra to determine the charge on the carbon atom, and that will be +4 in this case. Okay? And using our rules, and then of course just the simple addition, if oxygen is -2, that means hydrogen is +1. Okay? So now we can easily look at what has changed. We know that carbon went from a -4 to a +4. Okay? And oxygen has gone from a 0 to a -2. And it doesn't matter what oxygen you lead it to, it's definitely changed. Okay, so now that we know our oxidation state has changed, we're going to try to determine if these elements have lost or gained electrons based on their change in oxidation state. So a simple analogy is think about -4. You have 4 more electrons associated with this atom than electrons. Now with an oxidation of +4, you have 4 more protons associated with this carbon atom than electrons. So we go from -4, 4 extra electrons, to +4, a net loss of 4 electrons. We've actually lost 8 electrons in this process, but overall we've definitely lost electrons. Okay, oxygen's gone from a 0 to a -2. The oxidation state has gone down to -2. That means it has gained 2 electrons in this process. Okay, now we want to determine which one is the oxidation, which one's the reduction reaction. So we asked Leo. Leo is losing electrons, is oxidation. So this is our oxidation half reaction. And gaining electrons is our reduction. Okay. Okay, so now another set of terminology.